Module 5, Lecture B, Transfer Learning. By the end of this lecture, you will be able to load pre-trained vision models from torchvision and adapt them to new classification tasks, configure layer freezing and unfreezing strategies to balance training speed and performance, and fine-tune a pre-trained model on a custom dataset and compare results to training from scratch. Using pre-trained models. Torchvision models overview. In modern computer vision, it is common to start with a pre-trained model from libraries like torchvision, which provide convolutional and transformer-based networks trained on large datasets such as ImageNet. Models like ResNet, VGG, EfficientNet, and MobileNet have already learned powerful and general visual features. You can adapt these pre-trained models to tasks such as classifying medical images or detecting plant diseases. This approach lets you reuse their broad visual understanding and quickly tailor them to your specific problem. Torchvision models are like a toolbox of neural network architectures that trade off accuracy, speed, and memory in different ways. Lightweight options such as MobileNet and smaller ResNets are designed for limited hardware and real-time use on devices like phones or drones. More complex models, including deeper ResNets and large vision transformers, need stronger compute but can achieve higher accuracy, making them better for powerful GPUs or cloud systems. Torchvision makes it easy to switch between these models so you can compare their performance on your data and choose the one that best fits your constraints. Torchvision models are designed for transfer learning by separating a general feature extractor from a task-specific head. The feature extractor turns images into high-level visual representations, and the head converts these into final predictions. Because the extractor is pre-trained, it captures visual patterns that are useful across many domains. You can keep this pre-trained part and replace or adjust the final layers to match your own categories, allowing you to reuse the same architecture for different tasks while benefiting from large-scale pre-training. Python code. Torchvision models overview. This script gives an overview of model concepts similar to those in the torchvision library, but implemented with TensorFlow models. It focuses on how to load models that come with pre-trained weights and how to adapt them for new tasks. The goal is to simulate a typical torchvision-style workflow while working entirely within the TensorFlow ecosystem. In this environment, TensorFlow is already installed and ready to use, so you do not need to run any installation commands. The commented instruction about using pip is only there as a reminder of how you would install TensorFlow if it were not provided by default. Including such a comment is a common way to make sure the required library is available before running TensorFlow-based code. We begin by importing a few key modules needed for our script. The operating system module lets us work with files and the environment, and the random module provides tools for generating random numbers for tasks like shuffling or sampling. We also import NumPy for efficient numerical computations with arrays. Finally, we bring in TensorFlow, which we will use to build and train machine learning models as we create a TensorFlow-based overview similar to what torchvision offers. We set a seed value, such as 42, so that all random operations give the same results every time the code runs, which is important for reproducibility. We apply this seed to the random module so its random numbers are consistent. We also set the seed for the NumPy random number generator, so any random arrays or values it creates are repeatable. Finally, we set the seed for TensorFlow so its random behavior, like initial neural network weights, is the same on each run. Using the same seed across these libraries makes debugging and comparing results more reliable. This line displays the version of TensorFlow that is currently in use. It provides a quick way to check which version of the library is loaded. Knowing the exact version is important because different versions may behave differently. This helps with ensuring compatibility and makes debugging easier. In this example, we create a small synthetic image dataset with 3 classes, meaning it contains 3 distinct categories. Each image is set to be a square, with a height and width of 64 pixels. We also define the images to have 3 channels, so they are color images with red, green, and blue information. We begin by choosing to create 60 samples, which determines how many synthetic images we will generate. Using TensorFlow's random uniform function, we then create a block of random image data with the appropriate height, width, and number of channels. Next, we generate random labels for these images with another call to the random uniform function, this time shaped by the number of samples and limited by the number of classes, so the labels are valid integers. The result is a small, fully random dataset of images and corresponding labels that we can use for demonstration purposes. We convert the labels into a format suitable for classification by using a TensorFlow Keras utility that turns integer labels into one-hot encoded vectors. In this format, each label becomes a vector whose length equals the number of classes. The position that corresponds to the correct class is set to 1, and all other positions are set to 0. This representation is essential because it allows a classification model to learn and output a probability for each possible class. We begin by choosing a training set size of 40 samples, which gives us a simple way to separate training and validation data. We then take the first 40 images as our training inputs and the first 40 one-hot encoded labels as the matching training targets. This creates a defined subset of data for the model to learn from, while the remaining samples are reserved to check how well the model performs on unseen data. To create the validation subset, we use the remaining samples that come after the training portion of the data. We select the images starting from the index equal to the training size to form the validation images. And we do the same with the one-hot encoded labels to get the matching validation labels. This way, the validation set does not overlap with the training set. As a result, we can more reliably evaluate how well the model performs on data it has not seen during training. We begin by printing the shapes of the training and validation datasets to confirm that the data has been split and formatted correctly. This check verifies that each set has the expected number of samples and features. By ensuring the input dimensions match what the model expects, we reduce the risk of errors later in the training process. This simple step helps validate the data setup before moving on to model building. We are creating a small feature extractor similar to those used in common vision backbones by using the MobileNetV2 model from TensorFlow Keras applications. We set the input shape to match our image height, width, and color channels so the network can process our data correctly. By turning off the top classification layers, we keep only the convolutional base and can later attach our own custom classification head. We also start with no pre-trained weights, so the model begins with random parameters and can be trained specifically for our task. We use a global average pooling layer from the Keras library to reduce the spatial dimensions of the feature maps produced by the base model. This layer compresses each feature map into a single value by taking the average of all its values. Doing this simplifies the data while keeping the most important information. It also provides a smooth transition from the convolutional layers to the fully connected layers, preparing the output for the final classification head. For this classification task, we add a new output layer using a dense layer from the Keras library in TensorFlow. The number of units in this layer matches the number of classes we want to predict. We apply the softmax activation function so the outputs form a probability distribution over all classes. This setup is standard for multi-class classification problems. We build the model by first defining an input layer that matches the image dimensions, including height, width, and color channels. These inputs are passed into a MobileNetV2 base model, which is kept frozen so its weights are not updated, and it serves as a fixed feature extractor. The resulting feature maps are then reduced with a global average pooling layer, which compresses them into a single feature vector. Finally, this vector is fed into a dense classification layer with a softmax activation that outputs the class probabilities, completing the model architecture. Using TensorFlow's Keras interface, we define a complete model object that connects the input layer all the way to the output layer. This links the flow from the input image data through the feature extraction and classification parts of the network. By doing this, the entire neural network architecture is contained in a single model object. That model can then be compiled, trained, and evaluated as one unified system. We print the total number of layers in the model to quickly gauge its overall complexity and structure. This simple check tells us how many layers are involved in processing data, from feature extraction through to classification. Knowing the layer count helps us better understand and reason about how the model is organized and how it performs its tasks. We compile the model to define how it will learn during training. We use the Atom optimizer with a learning rate of 0.001 to control how much the model's weights change at each step. The loss function is categorical cross-entropy, which is appropriate for multi-class classification because it compares the predicted label distribution to the true labels. We also track accuracy as a metric to monitor how well the model performs during training and evaluation. We briefly train the model to adapt a pre-trained backbone by calling its fit method with training data and labels, along with separate validation data and labels to track performance on unseen examples. The training runs for 2 full passes over the training set, known as epochs. We use a batch size of 8, meaning the model updates its internal parameters after processing 8 samples at a time. The training output is silenced by setting the verbosity to 0 so that no progress messages appear in the console. We evaluate the model using a separate validation set, comparing its predictions with the true labels. This evaluation produces 2 main metrics: validation loss and validation accuracy. The loss shows how closely the predictions match the actual labels, while the accuracy gives the fraction of predictions that are correct. Setting the verbosity level to 0 makes this evaluation run silently without printing extra information. We report the validation loss by converting it to a float, rounding it to 4 decimal places, and printing it so we have a clear measure of how well the model fits the validation data. We then do the same for validation accuracy, again converting to a float, rounding to 4 decimal places, and displaying the result. Together, these rounded values give a concise and easy-to-interpret summary of the model's performance on the validation set. This script shows a simple workflow for adapting a TensorFlow model in a style similar to torch vision models. It begins by fixing a random seed and creating a small synthetic image dataset, which is split into training and validation sets. A MobileNetV2 network without pre-trained weights is used as a feature extractor, and a basic classification layer is added on top. The model is compiled with the Atom optimizer and a categorical cross-entropy loss, then trained briefly for 2 epochs to simulate adapting a backbone. Finally, it is evaluated on the validation data to report loss and accuracy, illustrating the full process of building, training, and assessing a model in a compact example. Model weights metadata. When using pre-trained vision models, the metadata attached to the model weights is essential because it describes how the model was trained and how it expects data. In modern torch vision, choosing a specific weights configuration gives you information about the training dataset, the training procedure, the required input normalization, and the class labels. For example, a ResNet trained on a large image dataset expects RGB images normalized in a particular way and produces outputs aligned with a fixed set of object categories. Understanding and respecting this metadata is crucial so you reuse the model correctly and do not break its input or output assumptions in new applications. Understanding the original label space in a model's weights metadata is essential when adapting a pre-trained model to a new task. This metadata tells you how many classes the model was trained on and in what order, so you can correctly align its outputs with your new labels. Knowing what the model originally learned to distinguish helps you judge how well it might transfer, such as when moving from consumer object recognition to retail tasks or from satellite imagery to land classification. This context guides you in selecting the most suitable pre-trained model variant for your specific application. Weights metadata describes how data was pre-processed during model pre-training and how the model performed, and it is critical for reliable adaptation. It records details like input size, color space, normalization, and metrics such as top 1 and top 5 accuracy. By following these pre-processing settings, you ensure the model's learned features behave as intended and avoid errors from mismatched data. The reported performance metrics also give a baseline to check whether your adapted model and data pipeline are working correctly. In sensitive areas like medical imaging or autonomous driving, respecting this metadata can be the difference between successful transfer learning and repeated failures. Python code, model weights metadata. This script introduces the basic ideas behind model weights metadata. It uses TensorFlow tools to mimic the style of metadata commonly seen in torch vision models. The goal is to help you understand how metadata about model weights is structured and used, without focusing on heavy or complex training procedures. The script includes an optional command to install the TensorFlow datasets library in case it is not already available in your environment. This library provides a collection of datasets that you can use to train and test machine learning models. The command is commented out by default, so it does not run automatically. You can enable it when needed to make sure the required datasets are accessible. We begin by importing 3 standard Python libraries: OS, Random, and Sys. The OS library lets us work with the operating system, for example by managing files or reading environment settings. The Random library is used to generate random numbers, which is important when we want experiments to be reproducible by controlling the random seed. The Sys library gives access to system-level information and tools, such as command line arguments and settings that affect how Python runs. We begin by importing TensorFlow, a powerful library used to build and train machine learning models. In this script, TensorFlow helps us create simple image model utilities that simulate metadata similar to what is available in torch vision models. This setup is important because it lets us define and manipulate neural network components, such as layers and complete models, which we will rely on later in the script. We set the random seed to a fixed value using the random library so that any random operations in the script always produce the same results each time the code runs. This consistency is important for reproducibility because it lets us repeat experiments and get identical outcomes. By fixing the seed, we can reliably compare results across different runs and computing environments. We set the random seed in TensorFlow to a fixed value, such as 42, so that any operations involving randomness will behave the same way every time the code runs. This makes the results repeatable instead of changing from run to run. Ensuring this kind of reproducibility is important when we want to compare experiments or reliably reproduce outcomes from the same script. This line of code prints the version of TensorFlow currently in use, which helps you quickly confirm that your environment is set up correctly. Checking the version is important for making sure your code is compatible with the installed library. It is also useful for debugging and for knowing which TensorFlow features and functions are available in your current setup. We define a metadata dictionary to describe a ResNet-like model, similar to what is used in common vision libraries. It records that the architecture is based on a ResNet-style design, and that the training dataset is a smaller version of CFAR 10. The metadata also states that the model predicts 10 classes, matching the 10 categories in the dataset. In addition, it specifies that input images are 32 by 32 pixels with 3 color channels, corresponding to red, green, and blue. We update the metadata dictionary to store normalization statistics, specifically the mean and standard deviation for each input channel. These values are used during pre-processing to normalize the data in a consistent way. Proper normalization helps ensure that the model receives well-scaled inputs, which supports stable training and reliable performance during both training and inference. We update the metadata dictionary to store the list of label names, which define the categories in the dataset and clarify what each class represents. We also record the training recipe version, here marked as version 1 with basic augmentation. This version label describes the preprocessing and augmentation techniques used during training and provides important context for how the model was trained and how that might influence its performance. We update the metadata dictionary to record 2 accuracy metrics from the original benchmark. The first is top 1 accuracy, set to 0.92, which measures how often the model's single most likely prediction is correct. The second is top 5 accuracy, set to 0.995, which measures how often the correct class appears within the model's 5 most likely predictions. Storing these values helps us understand the model's performance and compare it with other models. This code retrieves and prints the original dataset name stored in the model's metadata. Knowing this dataset name makes it easy to see what data the model was first trained on. This information is helpful when deciding how to reuse the model or adapt it for new tasks. The code reads the input size value from the model's metadata to find out what image dimensions the model expects. This gives a quick reference for how large the input images must be. Using this information helps ensure that all data sent into the model is correctly sized, which maintains consistency and prevents processing errors. The code prints the channel mean values stored in the metadata, which are used to pre-process images. These means help normalize the input data by centering pixel values around them. Doing this makes the input format more consistent, which supports more stable training and can improve the model's performance. We first print how many classes are defined in the metadata dictionary to see how many distinct categories the model is expected to classify. Then we display the first 3 class labels to get a quick sense of the kinds of objects the model can recognize. Together, these steps give a brief overview of the dataset size and the types of categories it covers. To illustrate the classification task, we briefly inspect a few example labels from the original dataset. The code retrieves the list of class names stored under the labels entry in the metadata and selects the first 3 items. Seeing these initial labels gives a quick sense of the kinds of objects the model was originally trained to recognize and helps orient us to the problem it is solving. This code prints the top 1 accuracy stored in the ResNet-like model's metadata. That value shows how often the model correctly predicts the single most likely class for each input. It serves as a quick summary of how well the model performed on its original benchmark dataset. In this step, we define a new set of labels for transfer learning by creating a list with the categories cat, dog, and horse. This narrows the model's focus from a broad set of classes to a smaller, more specific classification task. By doing so, we adapt the existing model to a new application where only these 3 classes are relevant. This relabeling is essential for tailoring the model's predictions to the new problem. We find the number of classes in a new label set by taking the length of the list of labels. This tells us how many distinct categories the model needs to predict. Knowing this count is essential, so we can adjust the model's output layer to have exactly 1 output unit per category. In this way, the model is correctly adapted to the new classification task. We begin by defining the model's input layer using the Keras tools in TensorFlow, making sure its shape matches the image dimensions described in the metadata. In this case, the input is set to images that are 32 pixels high and 32 pixels wide, with 3 channels to represent color. This configuration ensures that the model's input layer is fully compatible with the expected image data and can correctly process images with these characteristics. In this setup, we simulate a frozen backbone by applying a global average pooling layer to the inputs. This layer compresses each feature map by taking the average of all its values, summarizing the spatial information into a single number. As a result, it produces a fixed size output regardless of the input dimensions. This fixed size representation is especially useful for feeding into a dense layer in a classification head. We add a new classification head to the model to handle our custom labels. This head is a dense or fully connected layer built with Keras. Its number of units is set to the number of classes we want to predict, so the model's output matches our label set. We use a softmax activation so the outputs become probabilities over these classes. This dense layer takes as input the features produced by the backbone, which processes the data before it reaches the classification head. We build a new model by combining a pre-trained backbone with a custom head. The backbone processes the input data and provides useful learned features, while the head is a new layer that classifies the data into our specific categories. Using the Keras model function in TensorFlow, we connect the defined input layer to this new output layer. This approach lets us reuse powerful pre-trained features and adapt the model to our particular task with a tailored classification head. The code checks the output shape of the new model head to confirm it matches the expected size for the new label set. This ensures the model's architecture has been correctly updated to handle the labels cat, dog, and horse. By printing the output shape, we verify that the final layer produces predictions for the correct number of classes. This check is crucial for the model to perform accurate classification on the new label space. The code prints a confirmation message showing that the metadata has successfully guided how the model was adapted. It emphasizes the new labels chosen for the transfer learning task, which are cat, dog, and horse. This output acts as a final check that the model's configuration matches the intended changes. In other words, it verifies that the model is now set up to recognize these specific categories based on the provided metadata. This script shows how to use TensorFlow to work with model weights metadata rather than to train a model. It creates a reproducible setup, then defines a metadata dictionary for a ResNet-style model that includes architecture details, dataset information, normalization statistics, and benchmark accuracy. The script prints key fields such as the dataset name, input size, channel means, number of classes, and example labels, and then uses this information to guide transfer learning. It defines a new label set, builds a simple classification head with the Keras API, and attaches it to a simulated frozen backbone. Finally, it checks that the model's output shape matches the new label space, illustrating how metadata can drive correct model adaptation. Input size constraints. When using pre-trained vision models, you must match the input image size and shape to what the model was trained on. These models usually expect square color images with 3 channels for red, green, and blue. If you feed in images with different resolutions or grayscale channels, the model's layers may not line up correctly, leading to errors or weak performance. Even if your framework resizes images for you, it is your responsibility to ensure that pre-processing matches the model's original design so its accuracy is preserved. Input size limits in vision models are important for both accuracy and efficiency. Many models are trained on a fixed image resolution, such as 224 by 224 pixels, so their filters are tuned to that size. Making images larger usually just increases computation without improving accuracy, while making them too small can remove important details and hurt predictions. In real applications, such as plant disease classification, images should be resized to the model's expected input size while still keeping the key visual information needed for correct recognition. When adapting a pre-trained model to a new task, you must match your input size to what the architecture expects. Some models accept flexible input resolutions, while others require a fixed size. So high-resolution data like satellite images must be checked for compatibility with the model's design and weights. In practice, you usually standardize inputs to the model's preferred size using cropping or padding. You then fine-tune the model so its filters adjust to the new data patterns, ensuring it works effectively for your specific task. Python code input size constraints. This script demonstrates how image input size constraints work in TensorFlow. It examines how images are resized and represented as tensors, and then inspects their shapes. The key idea is that many models require images to have specific input dimensions, so understanding and checking these tensor shapes is essential. By focusing on the resized image tensors, you can ensure that your data matches what the model expects. The commented line is reminding you to install TensorFlow, a widely used library for machine learning and deep learning. Having TensorFlow installed is necessary because the rest of the script depends on it. In particular, the script uses TensorFlow to handle image processing and resizing tasks, so the environment must have TensorFlow available for the code to run correctly. We begin by importing a few standard libraries that the script will rely on. The operating system library lets us work with things like file paths and environment settings. The random library provides tools for generating random numbers, which we need for creating random data or modeling chance processes. We also import the numerical computing library NumPy, which we will use throughout the script to create and efficiently manipulate arrays. We begin by importing TensorFlow, a key library for machine learning and deep learning, along with the image-related layers from Keras. These tools provide the main building blocks for creating neural networks that can process and transform image data. Using these imports, we can handle images properly and prepare them as inputs to our models, such as by resizing them to match the dimensions a model expects. We start by choosing a seed value, such as 42, to control all random operations in our code. Setting this seed for both the standard random module and for NumPy's random number generator makes the random numbers and arrays they produce repeatable each time the program runs. This deterministic behavior is essential for reproducibility because it allows us to get the same results again. It is also very important for debugging and for reliably comparing different runs of an experiment or analysis. We begin by checking and printing the current TensorFlow version. This step helps confirm which version is installed so we know what features and syntax are available. Because different TensorFlow versions can change functions or behavior, knowing the exact version is important for compatibility. It ensures that the code we write or run will match the capabilities of that specific release. We use a small helper function to describe the shape of a tensor. It takes a descriptive name and the tensor itself, then retrieves the tensor's shape. The function prints the name along with the shape, converted to a tuple, so it is easier to read. This makes it convenient to quickly inspect and verify tensor dimensions during processing. We begin by choosing a standard input size for images so they match what common vision models expect. In this case, both the height and width are set to 224 pixels, a typical choice for models trained on datasets like ImageNet. We also use 3 channels to represent red, green, and blue, which is the usual format for color images. This setup ensures that any image we process has the correct dimensions and color format for these models. We create a dummy color image by defining its size as 300 pixels high and 400 pixels wide, then filling it with random pixel values. These values range from 0 to 255, which is the standard range for 8-bit color channels. The image has 3 channels that represent red, green, and blue, and its data type is set to unsigned 8-bit integers, which is appropriate for storing image data. We begin by converting the image from a NumPy array into a TensorFlow tensor, because TensorFlow operations work on tensors rather than NumPy arrays. During this conversion, we cast the image data to a floating point type, so it is compatible with TensorFlow's processing requirements. This prepares the image for later steps, such as resizing or passing it into a neural network model. We call a helper function to describe the tensor, giving it the label original along with the image tensor. The function prints this label followed by the tensor's shape, so we can clearly see the image dimensions. This step lets us verify the initial state of the image data before we apply resizing or any other transformations, ensuring we know exactly what we are starting with. We use a resizing layer from TensorFlow's Keras library to automatically adjust input images to a fixed size of 224 by 224 pixels. This step standardizes all images so they match the dimensions expected by many vision models. By resizing images in this way, we ensure they are properly preprocessed before being passed into the model. To prepare an image tensor for a vision model, you first add a batch dimension so it has the shape the model expects. After this expansion, you pass the tensor through a resizing layer. The resizing layer changes the image dimensions to the model's required input size. This process ensures the image has the correct shape and size for further processing or for use as model input. The code uses TensorFlow's squeeze function to remove the batch dimension from the resized tensor. This operation drops the first dimension, which is normally reserved for batches in machine learning models. As a result, the tensor's shape is simplified and matches the expected input shape. This makes the data easier to display and to use in further processing steps. We now check the shape of the resized tensor to verify that the image has been adjusted to the correct dimensions. This confirmation step is important to ensure the resizing worked as intended. By using a helper function to print the tensor's shape after resizing, we can confirm that it matches the input size expected by the model. We first define the expected shape of the resized image tensor, including its height, width, and number of channels, because many models require inputs with specific dimensions. We then compare the actual shape of the resized tensor to this expected shape. If they do not match, we raise an error to signal the mismatch. This check helps ensure that image preprocessing produces correctly shaped data and prevents failures when the model runs. We create a grayscale image using NumPy by generating random pixel values between 0 and 255, which is the usual range for image data. The image size is set by the original height and width, and we use a single channel to represent grayscale instead of separate color channels. This simple setup lets us focus on how images with only one channel are treated during the resizing process. We start with a grayscale image stored as a NumPy array and convert it into a TensorFlow tensor so it can be processed by TensorFlow operations. The image's pixel values range from 0 to 255, and we set the data type to 32-bit floating point. This data type choice ensures the image is compatible with TensorFlow's computation requirements. The code calls a function to display the shape of a grayscale tensor, which represents an image with only one channel instead of the 3 channels used in a typical color image. Viewing this shape tells us the image's dimensions. This helps us understand the data's structure before we perform any further processing or adaptation. We check the shape of the tensor after converting a grayscale image to an RGB-like format. This is important because the original grayscale image has only one channel, while an RGB image has 3. By repeating the single channel 3 times, we create a 3-channel tensor that behaves like a true RGB image. This allows the converted grayscale image to be processed in the same way as other color images in the pipeline. We start with a grayscale image that has been converted to an RGB format by copying its single channel into 3 channels. To prepare it for model input, we must resize it to the required dimensions of 224 by 224 pixels using a resizing layer. Before resizing, we add a batch dimension so the image tensor has the correct shape for the operation. This process ensures the image is properly formatted and sized for further processing or input to the model. We remove the batch dimension from the resized grayscale tensor using TensorFlow's squeeze function, which deletes any dimension whose size is 1. This simplifies the tensor's shape and makes it easier to view and manipulate. Removing the batch dimension is important so the tensor has the correct shape expected by later processing steps, or when it is passed into a model. The code prints a message to confirm the final shape of the resized grayscale image. It calls the print function to show a short label followed by the tensor's shape. This shape is taken from the tensor's dimensions and converted into a tuple. Hearing this output lets you know the exact final dimensions of the processed image. This script shows how to prepare images for TensorFlow models by enforcing consistent input sizes. It creates a random color image, converts it to a TensorFlow tensor, and uses a resizing layer to scale it to 224 by 224 pixels, a common size for vision models. It then verifies that the resized image has the expected shape. The script repeats this process for a grayscale image by first converting it to 3 channels to mimic RGB, then resizing and checking its shape. Overall, it demonstrates how proper image preprocessing ensures compatibility with model input requirements. Layer freezing techniques. Controlling requires grad. When using a pre-trained vision model, you can choose which parts of the network are updated by setting whether each parameter requires gradients. Parameters that require gradients are included in training and changed by the optimizer, while others stay fixed. By freezing early layers and only fine-tuning later parts, such as the final classification head, you lower computation and keep the useful knowledge learned from large datasets. This lets you adapt the model's decision-making to your specific task, like a new image classification problem, while still relying on its strong existing feature representations. When adapting a pre-trained convolutional network to tasks like satellite image classification, it is important to choose which layers are updated during training. Early layers learn general features such as edges and textures, so you can freeze their parameters to avoid unnecessary computation. You then allow gradients only in the deeper layers and the final classifier, so they can learn task-specific patterns, such as those found in different land types. This strategy speeds up training, reduces the amount of data needed, and focuses learning on refining existing representations instead of training the entire model from scratch. Controlling which parameters require gradients is a strategic way to balance training speed and model performance. If your data is similar to what the model was originally trained on, you can freeze most layers and only train the final ones for fast convergence and reduced overfitting. For data that is very different, you may need to gradually unfreeze more layers so the model can learn new patterns. A practical approach is to start with many layers frozen, watch validation performance, and unfreeze deeper layers if the model appears underfitted. This lets you carefully trade off computational cost, training stability, and how well the model adapts to your specific data. Python code. Controlling requires grad. This script conceptually demonstrates how to control the requires grad setting in a model. It uses simple flags to mimic freezing and unfreezing layers during training. The main goal is to show how these choices affect whether gradients are computed and how they flow through the network. By focusing on these decisions, it helps you understand and manage gradient behavior in a clear, simplified way. The script starts by explaining that TensorFlow is already available in this environment, so you can use it right away. It also notes that if you run the code somewhere else and TensorFlow is not installed, there is a commented instruction showing how to install it with a package manager. This step ensures that the required library is present so the code can run correctly. We begin by importing TensorFlow, a powerful library used to build and train machine learning models. Bringing TensorFlow into our script gives us access to its tools for defining models, creating layers, and performing the operations needed for deep learning. This single step enables us to use all of TensorFlow's core functionalities throughout our code. We use TensorFlow's random module to set a global random seed so that all random operations give the same results every time the code runs. This makes experiments reproducible, which is important when debugging models. It also allows fair comparison of model performance across different runs, since the randomness is controlled and consistent. This line displays the version of TensorFlow currently in use. It provides a quick way to confirm which version of the library is loaded. Checking the version helps ensure compatibility and that the code will behave as expected during execution. We use TensorFlow to create a small batch of dummy images for testing. This batch contains 4 images, and each image is 8 by 8 pixels with 3 color channels. All pixel values are set to 1. This simple setup lets us simulate how a model handles image input without needing real image files. We use TensorFlow's constant function to create a set of dummy labels for a 3-class classification task. These labels take the values 0, 1, 2, and 1, representing the different classes. The labels are stored with a 32-bit integer data type, so they are compatible with TensorFlow operations that expect integer class labels. We build a simple sequential convolutional vision model using the Keras interface in TensorFlow. It begins with a two-dimensional convolutional layer with a small number of filters and a ReLU activation to learn basic spatial patterns. A max pooling layer then reduces the spatial size of the feature maps to downsample the data and cut computation. We add a second convolutional layer with more filters and ReLU to extract richer features from this pooled output. Finally, a global average pooling layer compresses each feature map to a single value, summarizing spatial information and preparing the features for the classification head. We build a small classification head for a neural network that predicts 3 classes using a sequential model in TensorFlow Keras. It starts with a dense layer of 16 units with a ReLU activation to learn nonlinear patterns. Then, we add a second dense layer with 3 units, 1 for each class, using a softmax activation. This final layer outputs probabilities that sum to 1, making the model suitable for multi-class classification. We use TensorFlow's stochastic gradient descent optimizer with a learning rate of 0.1. This optimizer updates the model's parameters during training to reduce the loss function. By repeatedly adjusting the parameters in this way, it helps the model learn patterns from the data more effectively. In this step, we define a loss function using TensorFlow's sparse categorical cross-entropy, which is essential for training classification models. This loss measures how different the model's predicted class probabilities are from the true class labels. Because it works directly with integer labels, it is efficient and well-suited for multi-class classification tasks. By minimizing this loss during training, we guide the model to improve its predictions over time. The train step function runs a single training iteration while allowing control over which parts of the model are updated. It uses TensorFlow's gradient tape to record operations so gradients can be computed later for backpropagation. Within this context, it performs a forward pass on a batch of dummy images through the base model. This forward pass extracts features and runs the model in training mode so any training-specific behavior is properly activated. The code runs a forward pass through the model's classifier head using the features produced by the base model while in training mode. This step outputs logits, which are raw prediction scores before any activation function such as softmax is applied. These logits are essential for computing the training loss because they serve as the model's predicted outputs that are compared with the true labels. The code computes a loss value by comparing the model's predicted outputs called logits with the true labels, using a sparse categorical cross-entropy loss function. This loss measures how well the predicted class probabilities match the actual classes. The optimization process then uses this loss value to adjust the model's parameters so its predictions improve over time. We start by collecting the trainable variables from the base model, which are the parameters that can be updated during training. We then do the same for the classifier head, gathering its trainable parameters as well. Identifying these variables is important because it determines which parts of the model will receive gradient updates. This, in turn, lets us control whether certain layers are frozen or unfrozen during training. Here we create an empty list that will hold the model variables to be updated during training. By starting with an empty list, we can selectively add only the variables from layers that are not frozen. This lets us control which parts of the model receive gradient updates. As a result, we can fine-tune certain layers while keeping others fixed, depending on our training goals. This part of the code decides whether the base model should stay unfrozen during training. If it is not frozen, its trainable variables are added to the set of parameters that will receive gradient updates. This lets us control exactly which parts of the model are updated, making it possible to fine-tune certain layers while keeping others fixed as needed. This part of the code decides whether the classifier head should be trainable. If it is not frozen, its parameters are added to the set of variables that will receive gradient updates. This means the optimizer can adjust these parameters during training. As a result, the classifier head can continue learning, while other parts of the model can remain unchanged if desired. This code uses TensorFlow's gradient tape to compute how the loss changes with respect to the model's trainable variables. By doing this, it obtains gradients only for the parameters that are allowed to update. This is important because it ensures that frozen parts of the model remain unchanged. As a result, training respects the constraint that only selected parameters continue to learn while others stay fixed. When variables are selected for training, the optimizer updates them using the computed gradients. By applying each gradient to its corresponding variable, it adjusts the model parameters to learn from the data. This process ensures that every trainable variable is changed in the correct direction and by the correct amount based on its gradient. The function outputs the loss as a standard floating point number, so it is easy to read, log, and analyze. It does this by first using a NumPy conversion on the loss tensor to extract its single numeric value. That scalar value is then converted to a float, providing a consistent and simple format for working with the loss during further processing. In this training step, we keep the base model frozen, so its parameters do not change, and only allow the classifier head to be updated. This lets us see how performance improves when we adjust just the head while preserving the features already learned by the base model. It is a useful strategy for fine-tuning the model on new tasks without modifying the foundational layers. We create a stochastic gradient descent optimizer with a learning rate of 0.1 to update the model's parameters. Then we run a training step with both the base model and the classifier head set as trainable, meaning no parts of the model are frozen. During this step, the model performs a forward pass, computes the loss, and uses the optimizer to calculate and apply gradients to all trainable parameters. The resulting training loss is stored, so we can evaluate how the model performs when every layer is being updated. We first reset the optimizer to use stochastic gradient descent with a learning rate of 0.1 so that any previous state or momentum is cleared. Next, we run a training step with both the base model and the classifier head frozen, meaning no gradients are computed and no parameters are updated. This step still produces a loss value, which we record to see how the model performs when no learning takes place. In this training setup, the base model is kept frozen, meaning its parameters are not updated while only the classifier head is trainable. We track and print the loss value under this condition to observe how the training behaves. This shows how well the classifier head alone can adapt to the data when the underlying model remains fixed. The code prints the loss value when all layers of the model are set to be trainable, meaning both the base model and the classifier head are updated during training. In this setup, every parameter in the network is adjusted using the computed gradients. The loss value measures how closely the model's predictions match the true labels. By printing this loss, we can monitor how well the fully trainable model is performing as it learns to minimize errors. In this example, the code prints the loss value while both the base model and the classifier head are frozen, so none of the model's parameters are updated during training. Because all layers are frozen, the model does not learn from the data. As a result, its performance and the loss value stay essentially the same across training steps. This setup clearly demonstrates what happens when all layers are frozen and no learning occurs. We print the number of trainable variables in the classifier head when the base model is frozen to see how many parameters are still being updated during training. Since the base layers are not receiving gradients, only the classifier head continues to learn. By checking how many trainable variables remain in this head, we get a clear count of the parameters that are actively learning. This information is useful for debugging and for optimizing how we design and train the model. This script shows how to control gradient flow in a neural network using TensorFlow by freezing and unfreezing different parts of the model. It builds a simple convolutional base with a classification head and then runs 3 training scenarios. First, only the head is trainable while the base is frozen, so only the head's variables are updated. Next, both the base and the head are trainable, so all variables receive updates. Finally, everything is frozen, no variables are updated, and the loss does not improve. This demonstrates how choosing which layers receive gradients directly affects how the model trains. Feature extractor mode. In feature extractor mode, you use a pre-trained convolutional neural network as a fixed feature generator and train only a new classifier on top of its outputs. The pre-trained network acts like a sensor that has already learned useful visual patterns, and you keep its weights frozen while adjusting only the final layers. This greatly reduces the number of parameters you need to update, cuts computational cost, speeds up training, and lowers the risk of overfitting. It is especially useful when you have limited data, modest hardware, or tight time constraints, and need a quick, effective baseline model. In feature extractor mode, you keep the pre-trained convolutional backbone of a model and replace its original task-specific head with a new one suited to your classification problem. For example, you might use a model trained on a broad dataset, keep its early layers that capture general patterns, and attach a new classification head for your own categories. During training, gradients flow through the whole network, but only the new head's parameters are updated. This lets you reuse powerful pre-trained features while adapting the final decision boundary to your specific task. Feature extractor mode is most useful when your new task is similar to the original model's domain, or when you have too little data to safely fine-tune deeper layers. In areas like medical imaging or wildlife monitoring, where labeled data is scarce and expensive, using a pre-trained network as a fixed feature extractor can give strong performance with minimal data. This strategy offers a solid starting point and keeps training stable and efficient, while still allowing you to later fine-tune deeper layers if more data or accuracy needs arise. Python code, feature extractor mode. This script introduces the basics of using a model in feature extractor mode. It uses TensorFlow to demonstrate a simple form of transfer learning. The main idea is to freeze the existing layers of a pre-trained model, so their weights do not change. Then only the final classifier layers are trained on new data to adapt the model to a new task. The line with the exclamation mark is a command to install TensorFlow version 2.20.0. Using this exact version helps ensure the code runs correctly and remains compatible and reproducible. The exclamation mark also indicates that the command is intended to be executed in a Jupyter notebook or a similar environment that allows running shell commands directly from the notebook. We start by importing 3 key libraries for our script. The operating system library lets us interact with the system, for example, to work with files or environment settings. The random library provides tools to generate random numbers, which we can use for tasks like shuffling or sampling data. Finally, the numerical computing library NumPy gives us efficient support for working with arrays and performing mathematical operations throughout the program. We begin by importing TensorFlow, a library used to build and train machine learning models. Within TensorFlow, we use Keras, a high-level interface that makes creating neural networks easier. We also import the Layers module from Keras, which provides components like convolutional and dense layers. Together, these imports give us the essential tools to define and train neural network architectures efficiently. We begin by setting a seed value of 42, so that any random operations in our program are reproducible. We apply this seed to the random library, to NumPy's random number generator, and to TensorFlow's random operations. Using the same seed across these tools ensures we get identical results each time we run the code. This consistency is important for debugging and for reliably comparing results between different runs. We can check which version of TensorFlow is being used by reading its version attribute. Doing this confirms the exact release we are working with. Knowing the version helps us ensure compatibility with our code and understand which features are available in that specific setup. We begin by loading the MNIST dataset using Keras, which is a standard benchmark for image classification made up of handwritten digit images. The dataset is divided into training and testing sets, each containing images and their corresponding labels. We train our model on the training set so it can learn to recognize the digits. Then we evaluate its performance on the separate test set to check how well it generalizes to new, unseen data. To keep the runtime short, we work with a smaller portion of the dataset. We choose 2,000 samples for training and 500 for testing, then slice the training data and its labels so they only include the first 2,000 examples. This reduced subset allows the model to train faster while still providing enough data to learn useful patterns. We reduce the test data to a smaller subset by keeping only the first few samples, which lowers computational cost and speeds up testing. The same slice is applied to both the input images and their labels so they stay correctly matched. This way, we can evaluate the model more quickly while still using consistent and aligned test data. We first print the shapes of the training and testing datasets to confirm they match what we expect. This quick check verifies that the data has been loaded and split correctly. By doing this before any further processing, we reduce the risk of errors in later steps that depend on the correct data structure. We first convert the training images so each pixel is stored as a floating point number, which gives the precision needed for later calculations. Then, we normalize these pixel values to range between 0 and 1 by dividing by 255. This normalization keeps the input data on a consistent scale, which helps make training more stable and efficient. We apply the same conversion and scaling to the test images, so both training and test data are treated in the same way. Before using convolutional layers, we must add a channel dimension to the training and test data. We do this with a function that expands the data by adding an extra dimension at the end of each data point. This step is necessary because convolutional layers expect inputs to include a channel dimension, even for single-channel grayscale images like those in the MNIST dataset. By expanding the dimensions, we put the data into the correct shape for the convolutional neural network to process. We first print the shape of the training data after adding a channel dimension to confirm it matches the format expected by convolutional layers. This step verifies that each input now includes an explicit channel, which is required for these layers to work properly. We then do the same for the test data, checking its shape after expanding the channels. Together, these checks ensure that both the training and test datasets are correctly formatted for the next stages of processing. We define the input to our convolutional model as images that are 28 by 28 pixels with a single grayscale channel, similar to MNIST. We then add a two-dimensional convolutional layer with 16 filters of size 3 by 3. using the ReLU activation function to introduce nonlinearity so the model can learn more complex patterns. After this, we apply a max pooling layer with a 2x2 window to reduce the spatial size of the feature maps. This pooling step lowers computational cost and helps control overfitting by summarizing the most important features in each region. We extend the model with another two-dimensional convolutional layer that uses 32 small 3x3 filters and a ReLU activation to learn more complex features from the input. After this convolution, we apply max pooling with a 2x2 window to shrink the spatial size of the feature maps. This pooling step reduces computation and helps control overfitting by keeping only the most prominent features. We first flatten the multi-dimensional output from the previous layer into a one-dimensional array so it can be passed into the next dense layer, which requires a flat input. Then we add a dense layer with 64 units and a ReLU activation function to act as a fully connected layer that can learn complex patterns from these features. Finally, we define a Keras model by specifying its input and this dense output, creating the core backbone of the neural network that will be used to extract features from the data. We build a simple sequential model in Keras that stacks layers in order. The core of this model is a backbone network we defined earlier, which acts as a feature extractor. On top of this backbone, we add a dense layer with 10 units and a softmax activation, which serves as the classifier. This final layer converts the extracted features into probabilities for 10 classes, as in a digit classification task like MNIST. Training this setup quickly lets the backbone behave like a pre-trained model with learned features. To prepare the pre-training model, we first compile it by choosing key training components. We use the Atom optimizer, which is well suited for efficiently handling sparse gradients. We then set the loss function to sparse categorical cross-entropy, which matches multi-class classification problems where the labels are given as integers. Finally, we track accuracy as the main metric, giving a clear measure of how well the model is learning to classify the data during training. We briefly train the pre-training model on the labeled images to let it start learning useful features. The model makes a single pass through the entire training set, which is called one epoch. It processes the data in groups of 64 samples at a time before updating its weights. Training is run without displaying progress, and the main goal of this step is to give the model initial feature representations that will be used later for feature extraction. To use a model in feature extractor mode, we freeze the layers of the backbone so their weights no longer change during training. We do this by going through each layer in the backbone and marking it as not trainable. This keeps the previously learned features fixed and prevents them from being updated. As a result, only the new classifier head is trained, allowing it to learn from the stable, pre-trained features provided by the backbone. We begin by defining a new input layer for the model with a shape of 28 by 28 by 1 to match the image dimensions. This input layer becomes the starting point for the new classifier head we are adding. We then feed these inputs through the existing backbone model, making sure it runs in inference mode so its weights are not updated. In this setup, the backbone functions only as a fixed feature extractor for the new classification task. We extend the frozen backbone model by adding a dense layer with 32 units and a ReLU activation to learn more complex patterns from its extracted features. On top of this, we add another dense layer with 10 units and a softmax activation, which produces class probabilities for the 10 target categories. Using the backbone as input and this final softmax layer as output, we define a new Keras model that combines feature extraction with classification. We create a list of tuples where each tuple stores a layer's name and a Boolean value indicating whether that layer is trainable. To build this list, we iterate over all layers in the feature extractor model and record their trainable status. We then print a short message to introduce the output, followed by the list itself. This allows us to quickly verify which layers in the model are frozen and which remain trainable. We compile the feature extractor model to prepare it for fine-tuning. We use the Atom optimizer and choose sparse categorical cross-entropy as the loss function, which fits multi-class classification with integer labels. We also track accuracy as a metric to monitor performance during training. In this setup, only the new classifier head is trained, while the backbone stays frozen, allowing the model to adapt efficiently to new tasks. We train only the new classifier head while keeping the pre-trained backbone frozen, so the backbone's weights do not change. Using the feature extractor, we fit the model on the training images and their labels. The training runs for 2 full passes over the dataset and uses a batch size of 64 samples for each weight update. With verbose output turned off, this process quietly teaches the new head to make predictions based on the fixed features from the backbone. We now evaluate the feature extractor model on the test data by calling its evaluation function with the test inputs and their labels. This function calculates how well the model performs on unseen data by computing both the loss and the accuracy. It is run in silent mode, so it does not display progress while it works. The resulting loss value and accuracy score are then stored for later use and analysis. We report the feature extractor's performance using test accuracy, rounded to 4 decimal places for clarity. This single value gives a quick sense of how well the model performs on unseen data. It reflects the results after training the new classifier head while keeping the backbone of the network frozen. This script shows a simple feature extraction workflow in TensorFlow using the MNIST digit dataset. It loads and normalizes the images, builds a small convolutional neural network, and briefly trains it to act as a pre-trained backbone. The backbone layers are then frozen so they no longer update, and a new classifier head is added on top and trained on the same data. The script checks which layers remain trainable and evaluates the final model on a test set. The key idea is that the backbone stays fixed while the new classifier head learns to classify digits, illustrating how transfer learning can efficiently adapt a model to a task. Progressive layer unfreezing. Progressive layer unfreezing is a training strategy where you gradually allow more layers of a pre-trained vision model to be updated instead of training all layers at once. You begin by training only the new classification head, or top layers, while keeping earlier layers frozen so they preserve their general visual features. Once the classifier has adapted and the loss becomes stable, you slowly unfreeze deeper layers from the top down. This approach keeps useful representations learned from large datasets while still letting the model specialize to your domain, which helps avoid overfitting and prevents losing valuable pre-trained knowledge too early. In progressive unfreezing, you gradually unfreeze layers of a pre-trained model while carefully adjusting the learning rate and watching validation performance. You start by unfreezing only the top layers and use a relatively high learning rate so these layers can adapt quickly, while the frozen backbone stays stable as a feature extractor. As training stabilizes, you unfreeze more layers and lower the learning rate to avoid disrupting what the model has already learned. You continue this process until unfreezing additional layers no longer improves accuracy or begins to hurt generalization, which signals that you should stop. Progressive layer unfreezing is useful when you are limited by data, compute, or training time because it focuses learning where it matters most. You begin by training only the final classifier on top of a frozen pre-trained backbone. Then gradually unfreeze higher-level blocks so the model can adapt to the new task while early layers keep their basic pattern detectors. For small domain shifts, like a wildlife recognition app using a general image model, you may only need to adjust later layers. But for larger shifts, such as retinal scans, you unfreeze more layers slowly. This approach balances speed, stability, and performance, and lets you control how much pre-trained knowledge is preserved or changed. Python code, progressive layer unfreezing. This material demonstrates how to progressively unfreeze layers in a neural network model. It uses a small computer vision example built with TensorFlow to illustrate the idea. The focus is on how to initially freeze convolutional layers, then gradually unfreeze them so they can be fine-tuned. This approach helps control which parts of the model are updated during training. The commented line recommends installing TensorFlow version 2.20.0 to match the code being used. Specifying the exact library version helps avoid differences in features or behavior that can occur between versions. This practice keeps the software environment consistent and reduces compatibility problems when running the code in different places. We begin by importing a few standard Python libraries needed for the script. The operating system library lets us interact with files, folders, and other system features. The random library is used to generate random numbers and perform random operations, such as setting seeds or shuffling data. Finally, the numerical computing library NumPy provides efficient tools for working with arrays and carrying out mathematical calculations. We begin by importing TensorFlow, a library used to build and train machine learning models. Within TensorFlow, we use Keras as a high-level interface that makes creating neural networks easier. We also import the layer components from Keras so we can assemble different kinds of network layers, such as convolutional and dense layers. Together, these imports provide the basic tools needed to construct and train our neural network model efficiently. We begin by setting a seed value of 42 so that any random operations in our code are reproducible. This means we will get the same random results every time we run the program. To achieve this, we set the seed for the random library, then for NumPy, and finally for TensorFlow. Using the same seed across these libraries keeps the entire machine learning workflow consistent and repeatable. We begin by printing the TensorFlow version being used. This step helps verify that the environment is correctly configured and that the installed version matches what the script expects. It is important because different TensorFlow versions can have different features or behaviors. By confirming the version at the start, we make later debugging and compatibility checks easier. We begin by loading the MNIST dataset using a built-in Keras tool. MNIST is a standard collection of handwritten digit images used to train image recognition models. The data is divided into training images and labels, and separate testing images and labels. We train the model on the training portion, and then evaluate it on the testing portion to see how well it performs on new, unseen data. The code limits the number of training samples to 2,000 to create a smaller dataset. This reduced dataset makes training and testing faster, which is especially useful during development. By working with fewer samples, you can quickly try out different model settings and iterate more often. This approach helps you experiment efficiently without the heavy computation required for the full dataset. We limit the test set to 500 samples, so evaluation stays quick and manageable. For training, we also reduce the data size by keeping only the first 2,000 images and their labels. This smaller subset speeds up training and makes it easier to experiment and iterate on the model. In this step, we select a small subset of the test data by taking only the first few test images and their labels based on a predefined number of test samples. This reduces the amount of data we need to process and makes evaluation faster. Working with a smaller test set is especially helpful for quick checks, demonstrations, or early testing of a model's performance. The code converts grayscale MNIST images into 3-channel images by copying the single grayscale channel into 3 separate channels. This effectively turns each 1-channel image into a 3-channel format. This conversion is required because the convolutional neural network is designed to receive 3-channel inputs, similar to standard color images, even though the original data is grayscale. We first set the target image size to 32 by 32 pixels, which matches the input requirements of our convolutional neural network. We then resize all training images to this size using an image resize function, so they are compatible with the model. After resizing, we convert the images into NumPy arrays for further processing. We apply the same resizing and conversion steps to the test images to keep the training and testing data consistent. The image data is first converted to floating point numbers, then each pixel value is divided by 255, so that all values fall between 0 and 1. This normalization is important because it makes training a neural network more stable and helps it learn faster. The same scaling is applied to both the training and test data to keep the evaluation consistent with how the model was trained. We check the shapes of the training and test datasets to confirm they match what we expect. This simple step verifies that earlier pre-processing, such as resizing and normalizing the data, was applied correctly. By confirming the dataset shapes, we make sure the data is properly prepared and ready to be used for model training. To build a small convolutional backbone model, we define an input layer for 32 by 32 color images and pass it through a series of convolution and pooling operations. We first apply a 2-dimensional convolution with 16 filters and a ReLU activation, followed by max pooling to reduce spatial size. We then repeat this pattern with 32 filters and again with 64 filters, each time extracting more complex features while downsampling the feature maps. After the final convolution, we use global average pooling to compress each feature map into a single value, summarizing the spatial information. Finally, we create and name the Keras model using this input and the last process layer, producing a backbone network ready for further use. We begin by building a backbone model and keeping it non-trainable so its weights stay fixed during training. We define an input shape that matches the resized images with 3 color channels, then pass these inputs through the backbone to extract features. These features go into a dense layer with 10 units and a softmax activation to produce class probabilities for the 10 MNIST categories. Finally, we create the full model called MNIST Progressive by connecting the inputs to this classification head, allowing us to train only the new head while the backbone remains frozen. The model is now being prepared for training by choosing how it will learn and be evaluated. An Atom optimizer with a small learning rate is set up to adjust the model's weights and reduce errors. The loss function is defined as sparse categorical cross-entropy, which is appropriate for this kind of multi-class classification task. The model is also configured to track accuracy, so we can monitor how well it performs during both training and evaluation. We start by training only the new classification head of the model using the training data and labels. The model is trained for 2 epochs, so it goes through the entire dataset twice. A batch size of 64 is used, meaning the model updates its weights after processing 64 samples at a time. Training runs silently with no progress output and 10% of the training data is held out to validate the model's performance during training. After the first training stage, the model is evaluated on the test data to compute loss and accuracy, but these results are not shown right away. Instead, the accuracy value is rounded to 3 decimal places and then printed with a short message. This message explains that the reported accuracy reflects how well the model performs when only the new classification head has been trained, while all backbone layers remain frozen. Now, we start gradually unfreezing the deeper layers of the backbone model. We focus on the last 2 layers and switch their trainable setting to true. This allows these layers to be updated during training, so the model can fine-tune its deeper features. As a result, the model can adapt more effectively to the task and potentially achieve better performance. After unfreezing some layers, we recompile the model to adjust the learning rate so training remains stable. We use the Atom optimizer with a reduced learning rate of 5 times 10 to the minus 4 to avoid overly large weight updates. The loss function is sparse categorical cross-entropy, which is appropriate for multi-class classification with integer labels. We also track accuracy as a metric to monitor how well the model is learning during training. We now retrain the model with some backbone layers unfrozen so they can be updated during learning. The training function is called with the input data and labels, and we run for 2 epochs, meaning the model passes over the entire dataset twice. A batch size of 64 controls how many samples are used before updating the model's parameters. Training output is turned off, and 10% of the training data is held out as validation to monitor performance while the model trains. After progressively unfreezing some of the model's layers, we evaluate its performance on the test set using the model's evaluation function, which computes both loss and accuracy. We turn off detailed output during this step, so the process runs quietly. Finally, we report the test accuracy, emphasizing that it reflects the model's performance after unfreezing the later layers, and we round this value to 3 decimal places for clear presentation. The code checks how many layers in the backbone model are currently trainable by summing the true or false values of each layer's trainable setting. This sum gives the number of layers that are not frozen and can still be updated during training. It then prints this count after the second training stage, showing how many layers are actively being optimized at that point. This script shows how to use progressive layer unfreezing in TensorFlow on a small MNIST subset. It first builds a convolutional neural network with a frozen backbone and trains only the final dense classification layer for 2 epochs, then evaluates test accuracy to see how well this head performs on its own. Next, it gradually unfreezes the last 2 backbone layers, recompiles the model with a lower learning rate for stable fine-tuning, and trains for 2 more epochs before evaluating accuracy again, which usually improves. Finally, it reports how many backbone layers are now trainable, illustrating how to adapt a pre-trained model to a new task by slowly allowing more layers to update. Fine-tuning experiments. Dataset label mapping. When fine-tuning a pre-trained vision model, you must define a clear and consistent mapping between your class names and the numeric labels the model uses. Pre-trained models come with their own label spaces, but your dataset may have different or fewer classes, so you need to decide which integer corresponds to each class. This mapping must stay consistent across your data loading, loss function, and the model's final classification layer. If it is inconsistent, the model can learn the wrong associations, produce confusing predictions, and give misleading evaluation metrics, even if training appears to run without errors. Begin by defining all the classes your model must recognize, and assign each one a unique fixed index. When using a pre-trained model, replace its final classification layer so that the number of outputs matches your classes and their assigned indices. Make sure the model's output scores are ordered in exactly the same way as the labels in your dataset. If this mapping is inconsistent at any point in the pipeline, the model can learn the wrong associations, produce incorrect predictions, and give misleading accuracy results. Consistent label indexing is therefore essential for reliable model performance. When comparing a fine-tuned model to one trained from scratch, it is essential to keep the label mapping consistent so the results are truly comparable. If labels are mapped differently, class-level performance cannot be meaningfully compared, even when overall accuracy looks similar. This is especially important for ambiguous categories, where small changes in meaning can distort conclusions. To avoid these problems and make experiments reproducible, teams often maintain a shared label mapping document so that differences in performance reflect real model behavior rather than inconsistent labeling. Python code, dataset label mapping. This script demonstrates how to map dataset labels to their corresponding class indices. It uses TensorFlow image dataset tools to handle the images and their labels. The main goal is to clearly define and inspect how each class is indexed in the dataset. This helps ensure that labels are correctly understood and consistently applied during model training and evaluation. The command with the exclamation mark installs TensorFlow version 2.20.0. Specifying this exact version makes sure the code runs with the intended setup and avoids problems that can occur with different versions. This practice helps keep projects consistent and reliable across different systems and environments. We begin by importing 3 key libraries. The operating system library lets us work with the system environment, such as managing folders and file paths. The random library provides tools to generate random numbers, which is useful for creating random data or controlling randomness with a fixed seed. Finally, the numerical computing library NumPy allows us to create and manipulate arrays, which we will use to generate and handle random image data. We begin by importing TensorFlow, which we use to build and train machine learning models from data preprocessing through deployment. We also import the Layers module from Keras, the high-level interface within TensorFlow that makes it easier to construct neural networks. These layers provide common building blocks such as fully connected and convolutional components. With these imports in place, we are ready to define and train a neural network model using TensorFlow's tools. We set a fixed seed value, such as 42, to make our random operations reproducible. This seed is applied both to the standard random module and to NumPy's random number generator, so they each produce the same sequence of random values every time the code runs. Using a consistent seed is important for debugging and comparing experiments because it makes the behavior of any randomness predictable and repeatable. We set a global random seed for TensorFlow using the chosen seed value so that all random operations behave consistently each time the code runs. This makes the results repeatable, which is important for verifying experiments. It also helps with debugging because you can reliably reproduce the same behavior and track down issues more easily. This code prints the version of TensorFlow currently in use. Knowing the exact version helps you check compatibility, since different versions can change features or behavior. By displaying the version, you can verify that your environment is correctly configured for the tasks you plan to run and make debugging easier. We begin by creating a small directory called Tiny Animals Dataset, which will act as the main folder for all our data. Inside this structure, we define 2 image categories, cat and dog. These categories represent the classes of images we will use. Organizing the data this way makes it easy for TensorFlow to process the images and correctly link each one to its label. We first make sure the main folder for our dataset exists by calling the operating system's function that creates directories. This function will create the folder only if it is missing, and do nothing if it is already there. By doing this, we can safely organize and save our dataset without running into errors caused by missing directories. We create a separate subfolder for each class name inside a main base directory. For every class in our list, we call the operating system's makeDirectories function with a path that combines the base directory and the class name. We allow existing folders, so the function does not raise an error if a directory is already there. This structure organizes the dataset into one folder per class, which is a standard approach in image classification tasks. We define our images to be 32 pixels high and 32 pixels wide, with 3 color channels to represent standard RGB images. We then choose to create 3 images for each class. This gives us a small, well-structured dataset where every class has the same number of images. Such a balanced setup is helpful for both training and testing image models. This function creates and saves a random image at a specified location. It first builds a 3-dimensional array of random integer values between 0 and 255 and match the desired height, width, and number of color channels, representing the pixel data. It then uses a TensorFlow utility to convert this array into an image format. Finally, it writes the resulting image file to the given path. For each class name in the list, we build the folder path by combining the base directory with that class name, defining where that class's images will be stored. We then loop as many times as the number of images we want for that class. On each loop, we create a unique image file name using the loop index. Finally, we call the random image creation function with the full path, so the requested number of random images is generated and saved for every class in its own directory. We create a dictionary that assigns each class name a unique index by looping through the list of class names with an enumeration function that provides both the index and the name. This produces a fixed mapping, so the same class name always gets the same index every time the code runs. Such deterministic and consistent label mapping is essential for tasks like training models because it ensures that the model's predictions line up correctly with the intended class labels. We build an inverse mapping called index to label by reversing the original label to index dictionary. For each entry, we use the numeric index as the key and the class name as the value. This creates a direct way to translate numeric labels back into their class names. Having this reverse lookup is important for interpreting model predictions and understanding dataset labels in a human-readable form. The script first prints the mapping from each label to its index, showing how every class name is assigned a unique integer, so the model can work with categorical data. It then prints the reverse mapping from index to label. This second mapping lets us convert the model's numeric predictions back into readable class names. Together, these two mappings make it possible both to feed labeled data into the model and to interpret its outputs correctly. We load the image dataset using TensorFlow's utility that reads images from a base directory and automatically assigns labels based on folder names. To keep the label mapping consistent, we explicitly specify the class names. Each image is resized to 32 by 32 pixels with 3 color channels. We use a batch size of 2, so each batch contains 2 images, and we turn off shuffling while setting a fixed seed to ensure the data order is reproducible. We take a single batch of images and labels from the training dataset by advancing the dataset iterator. This gives us a small, manageable portion of the data that we can use right away. The main goal is to check that data loading works correctly and that the images and labels have the expected shapes. Confirming this before further processing or model training helps catch problems early and ensures the pipeline is set up properly. We begin by printing the shape of the image batch to check the dimensions of the loaded image data and confirm it matches what we expect. Then we print the shape of the label batch to verify that the number of labels matches the number of images. This ensures that every image has a corresponding label. These simple checks are important for debugging and confirming that the dataset is correctly structured before training a model. We start by turning the labels from the dataset into a list of unique values. To do this, we convert the TensorFlow tensor of labels into a NumPy array, then into a Python list. We then use a set to keep only the distinct label values and sort them to maintain a consistent order. This ordered list of unique labels is important because it lets us reliably map numeric labels back to their corresponding class names later on. The code goes through each unique numeric label in the dataset and prints it along with its matching class name. It does this by using a dictionary that maps each numeric index back to its class label. This process lets you check that every numeric label correctly corresponds to the intended class name. As a result, you can be confident that the label mapping is accurate before using the data for further processing or model interpretation. We first determine how many classes we have by taking the length of the class names list, since this tells us how many output categories the model must predict. Then we build a sequential model in Keras that starts with an input layer matching the image height, width, and color channels. The image is flattened into a one-dimensional array so it can be passed into dense layers. We add a dense layer with 8 units and a ReLU activation to let the model learn non-linear patterns. Finally, we use another dense layer with as many units as there are classes and a softmax activation, which produces a probability for each class so the model can choose the most likely label for an image. We begin by compiling the model to prepare it for training. We use the Atom optimizer, which is well suited for efficiently handling sparse gradients. The loss function is sparse categorical cross-entropy, which matches multi-class classification tasks where the labels are given as integers. We also track accuracy as the main metric to evaluate how well the model performs during both training and testing. We briefly train the model on the dataset to show how the label mapping works in practice. The training function is called with the training data for just one pass through the dataset, so the process stays short. Detailed training output is turned off to keep the demonstration simple. This step mainly serves to illustrate how the label mapping is integrated into the model's training procedure. The code evaluates the trained model on the dataset to measure how well it performs. It computes the loss and accuracy using the evaluation function, with detailed output turned off. The accuracy is then converted to a floating point number and printed. This process checks how well the model has learned the correct label mappings from the training data. This script shows how to map image labels in a TensorFlow dataset and verify that the mapping works correctly. It creates a small example with 2 classes, cats and dogs, assigns each class a fixed numeric index, and prints both the label to index and index to label mappings. The images are loaded into a TensorFlow dataset with labels inferred from the directory structure, then processed in small batches to confirm the shapes of the image and label tensors. A simple neural network with dense layers is built, compiled with sparse categorical cross-entropy, briefly trained on this dataset, and then evaluated. The output reports the TensorFlow version, the label mappings, the data shapes, and the model's accuracy, illustrating that the label mapping and training pipeline are functioning as intended. Choosing learning rates. When fine-tuning a pre-trained vision model, Choosing an appropriate learning rate is critical because it controls how much you change the original weights. If the learning rate is too high, the model can catastrophically forget useful features it previously learned. If it is too low, training becomes slow, especially when the new dataset is very different. The aim is to pick a learning rate that is low enough to preserve the pre-trained structure, but still high enough to adapt efficiently to the new task. When fine-tuning a model, it is often useful to use different learning rates for the pre-trained backbone and the new classification head. The new head starts with random weights, so a higher learning rate helps it quickly learn task-specific decision boundaries. In contrast, the backbone already encodes useful features, so it should use a lower learning rate to avoid overwriting what it has learned too aggressively. This strategy, called differential learning rates, allows the backbone to adapt gently while the new head learns the details of the target task. Choosing a learning rate is an experimental process with no single value that works for every model and dataset. When fine-tuning, start with a smaller learning rate for pre-trained layers than you would use when training from scratch. Then adjust based on training loss, validation accuracy, and signs of overfitting. Systematically vary the learning rates for the backbone and the head while keeping other settings fixed, and compare how quickly and how well each setup converges and generalizes. This helps you see whether the model is learning too slowly or overwriting its prior knowledge too quickly, so you can find a balance between stability and adaptability compared with training a model from scratch. Python code, choosing learning rates. This script compares how two different learning rates affect fine-tuning. It uses a very small convolutional neural network trained on a small subset of the MNIST dataset. The main goal is to observe how changing the learning rate influences the training behavior and outcomes. This command installs TensorFlow version 2.20.0, so the script uses that exact release of the library. Fixing the version helps prevent compatibility problems that can occur with newer or older versions. It is a standard practice in machine learning projects to specify library versions to keep behavior consistent across different systems and environments. We start by importing three key Python libraries. The operating system library lets the script interact with the system, for example, to work with files or environment variables. The random library is used to generate random numbers, which is useful when we need randomness, such as shuffling data. Finally, the numerical computing library NumPy provides efficient tools for working with large arrays and matrices, and in this script, it will handle and process the dataset. We start by importing TensorFlow, a library used to build and train machine learning models. Within TensorFlow, we use Keras as a high-level interface that makes creating neural networks easier. We also import the layer components from Keras so we can define different kinds of layers, such as convolutional and dense layers. Together, these imports provide the basic tools we need to construct and train a convolutional neural network on the MNIST dataset. We set a seed value of 42 to make our results consistent and reproducible. This seed initializes the random number generators in Python's built-in random module, in NumPy, and in TensorFlow. Using the same seed ensures that every run of the script produces the same sequence of random numbers. This consistency is crucial for reliable debugging and for fairly comparing different runs or models. This line displays the version of TensorFlow currently being used in the script. It provides a quick check that the intended version of the library is installed and active. Confirming the version helps ensure compatibility and that all features and functions work as expected. We begin by loading the MNIST dataset using the Datasets module in Keras, which provides separate training and test sets. Each set includes images of handwritten digits, along with their labels. The training data is used to teach the model to recognize patterns in the images, while the test data is kept aside and used only after training to evaluate how well the model performs on new, unseen examples. To quickly test different learning rates, we work with a smaller subset of the MNIST dataset instead of the full data. We choose 4,000 samples for training and 1,000 for validation. Then we slice the original training data to keep only the first 5,000 samples, which matches the total number we need. This reduced dataset speeds up experimentation while still allowing us to compare learning rates effectively. To prepare our data for model training, we split it into separate training and validation sets. We first take a portion of the original training data, starting at the index equal to the number of training samples, and use this part as the validation inputs and labels. Then we redefine the training data as all elements up to that index, which gives us the final training inputs and labels. This process ensures that the training and validation sets are distinct and do not overlap. To prepare the data for training a neural network, the image pixels are first converted to floating point numbers, then each value is divided by 255 so that all pixels fall between 0 and 1. This normalization helps the network train more efficiently and improves convergence. The same scaling is applied consistently to the training, validation, and test sets so that all parts of the dataset are processed in the same way. To prepare image data for a convolutional neural network, we need to add a channel dimension to the training, validation, and test sets. Convolutional layers expect inputs to include this channel dimension as part of their shape. For grayscale images, such as those in the MNIST dataset, this channel value is 1. We use a function from the NumPy library to expand the dimensions of each dataset so they match the format required by the model. We first print the shape of the training data and labels to confirm they are correctly formatted before building the models. This check makes sure the data dimensions match the neural network's expected input shape. Verifying this alignment early helps avoid shape mismatches and other errors during model training. We define a simple convolutional neural network to act as a feature extractor for grayscale images of size 28 by 28. It begins with a two-dimensional convolutional layer, using 16 filters with a small kernel and ReLU activation, followed by max pooling to reduce the spatial dimensions. A second convolutional layer with 32 filters and the same activation further captures patterns, and another max pooling layer continues the downsampling. The resulting feature maps are flattened into a one-dimensional vector and passed to a dense layer with 64 units and ReLU activation to learn higher-level representations. This sequence of layers is wrapped into a Keras model named Backbone, which is then returned for later training. We begin by building a backbone model that acts as a feature extractor for our data. We then compile this model using the Atom optimizer with a learning rate of 0.001. For the loss, we choose sparse categorical cross-entropy, which is appropriate for multi-class classification when the labels are given as integers. Finally, we track accuracy as the main metric to evaluate how well the model performs during training. To prepare the backbone model for pre-training, we attach a temporary classification layer on top, using a dense layer with 10 units and a softmax activation to produce class probabilities. We then define a new model that connects the backbone's input to this output layer, creating a complete classifier. This model is compiled with the Atom optimizer using a learning rate of 0.001. For training, we use sparse categorical cross-entropy as the loss function, which is appropriate for multi-class classification, and we monitor accuracy as the main performance metric. During pre-training, the model is fitted to the dataset by using the training images and their labels to adjust its parameters. The training process runs for 2 full passes over the data, so the model sees every image twice. It updates its parameters after processing groups of 64 images at a time, which is the batch size. The training is run in silent mode, so no progress messages are displayed while it learns. When fine-tuning a model, we usually freeze the backbone, which is the main feature extractor, so its weights do not change. By making the backbone non-trainable, its parameters stay fixed during training. This lets us train only the new layers added on top, while preserving the useful features learned during pre-training. As a result, the model can adapt to new tasks or data without forgetting its original knowledge. We build a fine-tuning model by defining an input layer for images that are 28 by 28 pixels with a single channel. Then, passing this input through a backbone network whose weights are kept fixed during training. The backbone's output is connected to a dense layer with 10 units and a softmax activation to generate class probabilities. We then create and name a Keras model using this input and output configuration, and return it for later use. We begin by building 2 identical models so we can compare different learning rates fairly. Using a fine-tuning function, we take the same backbone model and attach a classification head while keeping the backbone frozen. We do this twice to create one model that will use a low learning rate and another that will use a high learning rate. Because the models are structurally the same, any differences in training performance can be attributed to the learning rate choice. We define 2 different learning rates to compare how they affect model training. The low learning rate is set to 1 × 10⁻⁴, which makes parameter updates slow and stable. The high learning rate is set to 1 × 10⁻², which allows faster learning but increases the risk of skipping past the best solution. By using both, we can observe how each choice influences the model's performance during training. We compile the model using the Atom optimizer with a low learning rate to support stable convergence, which is especially helpful when fine-tuning. The loss function is sparse categorical cross-entropy, which is appropriate for multi-class classification tasks where the target labels are given as integers. We also track accuracy as a metric so we can monitor how well the model is performing during training. We now build a second model that is the same as the first one, but trained with a higher learning rate. We use the Atom optimizer and set its learning rate to this higher value defined earlier. The loss function is sparse categorical cross-entropy, which is appropriate for multi-class classification when the labels are given as integers. We also track accuracy during training, so we can monitor how well the model is learning to classify the data. We train the model using a lower learning rate and call the training function with our input data and labels. The model runs for 2 full passes over the dataset, updating its weights after every 64 samples. We also provide separate validation data, so we can track how well the model performs on unseen examples during training. The training is set to run silently without printing progress updates. We start training the model using a relatively high learning rate by calling the training function with our input data and labels. Pause. The model will train for 2 epochs, meaning it goes through the entire training set twice. A batch size of 64 is used, so the model updates its weights after processing each group of 64 samples. We also provide validation data to check performance on unseen examples after each epoch, and the training runs silently without printing progress updates. We evaluate the model that uses the lower learning rate on the validation data to measure its performance. Using the model's evaluation function, we compute the loss and accuracy for the validation set. These results are saved separately as validation loss and validation accuracy. The evaluation is run in silent mode, so no progress messages are printed while it runs. We now evaluate the model that was trained with a high learning rate using Keras' evaluation function on the validation data. This function takes the validation images and their labels as input and runs silently without printing progress. It returns two key metrics, the validation loss and the validation accuracy. These values are stored for later, so we can compare this model's performance with other training setups. This script prints a brief comparison of how different learning rates affect model accuracy. It reports the low learning rate along with its validation accuracy, rounded to 4 decimal places. It then reports the high learning rate and its validation accuracy in the same way. Together, these outputs give a quick view of how each learning rate influences the model's performance. This script shows how different learning rates affect training a small convolutional neural network on a subset of the MNIST dataset. A simple network is first briefly pre-trained to simulate a starting point. Then 2 identical models are fine-tuned with different learning rates, one very low and one relatively high, for the same number of epochs on the same data. After training, both models are evaluated on validation data. In most cases, the model with the lower learning rate reaches higher validation accuracy because it learns more steadily, while the higher learning rate can cause overshooting and poorer performance. The script finishes by printing the validation accuracies for both settings to highlight this difference. Comparing baselines. When fine-tuning a pre-trained vision model, you should always compare it to a strong baseline to get meaningful results. Use the same architecture trained from scratch with identical settings, including pre-processing and optimizer choices, so that pre-training is the only major difference. For example, if you are classifying plant diseases, train a convolutional network from the beginning and compare it to a version fine-tuned from a model pre-trained on a large image dataset. Any gains in accuracy or training speed can then be confidently attributed to the pre-trained weights rather than changes in the training setup. When evaluating your fine-tuned model, you should compare it not only to a model trained from scratch, but also to other realistic baselines. These can include simple deep learning models, such as small convolutional networks or compact vision transformers trained from scratch, as well as non-deep learning methods that use handcrafted features with classical classifiers. In some domains like medical imaging, existing practices such as manual assessments or rule-based systems are also important baselines. Comparing your model to these alternatives helps reveal its strengths and weaknesses and supports a stronger argument for its value in real-world use. When comparing a fine-tuned model to its baseline, look beyond a single performance metric and consider how quickly it learns, how sensitive it is to hyperparameters, and how robust it is to changes in the data. Fine-tuned models can often reach strong performance with fewer labeled examples, which is valuable when annotation is expensive. In contrast, models trained from scratch may work better when the target domain is very different from the data used for pre-training. By jointly evaluating accuracy, precision, recall, training time, and resource usage, you can judge whether fine-tuning truly offers an advantage for your specific task. Python code, comparing baselines. This script is designed to quickly compare simple computer vision baseline models. It uses TensorFlow to run these experiments efficiently. The main goal is to evaluate how well different models perform when they are trained entirely from scratch. The line that begins with an exclamation mark is a command to install TensorFlow version 2.20.0. It is commonly used in notebook environments to make sure the script runs with the correct TensorFlow version. In this case, the line is commented out, which suggests that installing TensorFlow may not be necessary here, or has already been done in the environment where the code will run. We begin by importing 3 key libraries for our script. The operating system library is included for potential interaction with the system environment, even though it is not directly used in this snippet. The random module is brought in to generate random numbers, which is important for setting seeds and making results reproducible. Finally, we import NumPy, a numerical computing library that will handle arrays and perform efficient mathematical operations throughout the code. We start by importing TensorFlow, a library used to build and train machine learning models. Within TensorFlow, we use Keras as a high-level interface that makes creating neural networks easier. We also import the layers module from Keras, which provides components like convolutional and dense layers. Together, these imports prepare the environment for efficiently defining and training deep learning models. To make our results consistent and reproducible, we set a seed value of 42 for all sources of randomness. We first use this seed to initialize Python's random number generator, so that any random operations give the same outcome each time. We then apply the same seed to the NumPy random number generator for any NumPy-based randomness. Finally, we set the seed for TensorFlow's random number generator, which is especially important in machine learning experiments where random weight initialization and other random processes can change the results. By aligning these seeds, we ensure that the entire experiment can be repeated with identical outcomes. This line of code prints the version of TensorFlow currently in use. It provides a quick check that the correct version of the library is installed. Confirming the version helps ensure that the code is compatible with TensorFlow and that any required features or functions are available. This simple check can prevent errors caused by version mismatches. We begin by loading the MNIST dataset using the Keras datasets module. MNIST is a standard collection of handwritten digit images used to train image processing models. The data is divided into a training set, which is used to teach the model, and a testing set, which is used to measure how well the model performs. Both sets contain images along with labels that indicate which digit appears in each image. To quickly test our model, we work with a smaller subset of the MNIST dataset instead of the full data. We choose 4,000 samples for training and 1,000 for testing, then keep only the first 4,000 training images with their labels, and the first 1,000 test images with their labels. By reducing the dataset size in this way, we speed up experimentation and can iterate on model development more quickly. In this step, we use only a subset of the test data to make evaluation faster and more manageable. We limit the test images to the first 1,000 samples and take the corresponding first 1,000 labels so they stay correctly matched. By working with this smaller aligned test set, we can efficiently check how well our model performs without having to process the entire dataset. The code first prints the shapes of the training and test datasets to verify that the data has been loaded and split correctly. This check confirms that there are 4,000 training samples and 1,000 test samples, each with matching labels. By validating these dimensions early, it helps detect any problems in the data preparation process before moving on to further analysis or modeling. The code prepares the training and test images by normalizing their pixel values. It first converts the image data to a float32 type to support stable numerical computations. Then it divides each pixel value by 255 so that all values fall between 0 and 1. This normalization keeps the input data on a consistent scale, which helps the neural network train more efficiently and converge more reliably. Before using convolutional layers, we must add a channel dimension to the training and test data. We do this by expanding the data arrays with an extra axis at the end. This step is essential because convolutional layers expect inputs to include a channel dimension. Even for grayscale images, like those in the MNIST dataset, we still need this single channel dimension so the data has the correct shape for the model. We check the shape of the training data to confirm that a channel dimension has been added, which is necessary for convolutional layers to handle the images properly. We also inspect the shape of the test data to make sure it follows the same expanded format. By verifying these shapes, we ensure that both training and test sets are correctly structured and ready to be fed into the convolutional neural network model. We define a simple convolutional neural network that takes a 28 by 28 grayscale image as input. It first applies a two-dimensional convolutional layer with 16 filters and ReLU activation, followed by a 2 by 2 max pooling layer to reduce spatial size. A second convolutional layer with 32 filters and ReLU activation is added. Then another max pooling layer for further downsampling. The resulting feature maps are flattened into a one-dimensional vector and passed to a dense layer with 64 units and ReLU activation to learn higher-level patterns. Finally, an output dense layer with 10 units and a softmax activation produces class probabilities for tasks such as digit recognition, and the function returns this constructed model. We begin by creating a baseline model using a previously defined function that builds a simple convolutional neural network, a standard architecture for image classification. Calling this function gives us a fresh model that we then train on our dataset. The performance of this trained model serves as our baseline. Later, we will compare other models against this baseline to see whether they offer any improvement. To prepare the baseline model for training, we first configure it with the Atom optimizer using a learning rate of 0.001. We then choose sparse categorical cross-entropy as the loss function, which is appropriate for multi-class classification when the labels are integers. Finally, we track accuracy as the main metric to evaluate how well the model performs during both training and testing. Together, these choices define how the model learns and how its success is measured. We train the baseline model using a fit function that takes the training data and labels. The model is trained for 3 epochs, meaning it passes through the entire training set 3 times. We use a batch size of 64, so the model updates its parameters after processing that many samples at a time. The training runs silently with no progress messages, and 10% of the training data is held out as validation to monitor performance during training. We evaluate the baseline model on the test subset to measure how well it performs on unseen data. The evaluation function runs on the test images and labels with no detailed progress output. It returns 2 key metrics: the loss, which reflects how well the model's predictions match the test data, and the accuracy, which is the percentage of correct predictions. Together, these values indicate the model's effectiveness on new examples. We begin by simulating a pre-trained model by building a new convolutional neural network with the helper function defined earlier. This function creates a simple architecture that includes convolution layers, pooling layers, a flattening step, and dense layers. Calling this function gives us a fresh instance of the model, which we can then train further and use as a basis for comparison with other models. We compile the pre-trained model using the same configuration as before, with the Atom optimizer set to a learning rate of 0.001 to update the model's weights during training. The loss function is sparse categorical cross-entropy, which is appropriate for this kind of multi-class classification problem. We also monitor accuracy as a key metric to assess how well the model performs during both training and testing. The pre-trained model is further trained on the same dataset by calling its training function with the input data and labels. It is run for 2 more passes, or epochs, over the data, using a batch size of 64, so it updates its parameters after processing 64 samples at a time. The training is run in silent mode, so no progress is printed. This extra training step is used to simulate a pre-trained model before it is later fine-tuned. We now fine-tune the pre-trained model for a few more training cycles. Using the training data and labels, we run the training process for 3 epochs, meaning the model sees the entire dataset 3 times. The batch size is 64, so the model updates its weights after every group of 64 samples. Training runs silently without progress messages, and 10% of the training data is held out as validation to track performance on unseen examples during training. We now evaluate the fine-tuned model on the test set to measure how well it performs. Using the Keras evaluation function, we provide the test inputs and their labels, and run it in silent mode so no progress messages are printed. This evaluation returns 2 key metrics, the loss value and the accuracy on the test data. By comparing these results with those from the original baseline model, we can judge how effective the fine-tuning process has been. We first report the test accuracy of the baseline model to see how well it performs before any extra training. Then we report the test accuracy of the fine-tuned model after additional training. By comparing these 2 accuracies and computing their difference, we can clearly see how much the fine-tuning process has improved the model's performance. This script compares 2 simple convolutional neural networks on the MNIST digit dataset to show the effect of pre-training. It prepares a small, normalized subset of the data, then trains a baseline model from scratch for a few epochs and records its test accuracy. Next, it simulates a pre-trained model by training a second network longer before fine-tuning it for the same number of epochs and evaluating it on the test set. Finally, it prints the accuracies of both models and their difference, typically showing a modest accuracy gain from the additional pre-training and fine-tuning. In this lecture, you learned to load pre-trained vision models from torchvision and adapt them to new classification tasks, configure layer freezing and unfreezing strategies to balance training speed and performance, and fine-tune a pre-trained model on a custom dataset and compare results to training from scratch. In the next module, Module 6, we will go over NLP with PyTorch. Thank you for your attention. See you all in the next lecture.